Right then, so the work problems for chapter 3. So let's go ahead and get the credits done. I'm going to have to give several for the work problems. So a lot of the problems are taken from Zumdahl's chemistry. Some are taken from Brown and LeMay's chemistry. Some are taken from Mr. Mack's AP chemistry work. Website. So that's a good place for you to go if you're familiar with all the ones that I've given you and you want some more practice. I would start off by going there. And occasionally, as I've said before, some will come from McMurray and Fay. So the answers are all from myself. Let's go to the next slide. So here are your credits. You can pause that if you want and look at that. Next slide. The solutions here are provided by myself. Next slide. All right, so here we go with number 1. What amount of moles are represented by each sample? The first two, they give you the grams, or they give you the ability to convert. And B, they give you milligrams, but that's not a problem. And then in C, they give you the number of molecules of BF3. So let's start with C. For part C, if we're told how many molecules we have of something, we just compare that with 6.02 times 10 to the 23rd. So we would divide here 1.5 times 10 to the 16th. We would divide by 6.02 times 10 to the 23rd, and that will give us the number of moles. So that's what we're supposed to give them, is the number of moles. So just divide for part C, 1.5 e 16 by 6.02 e 23. B, let's do it next. We have 10 milligrams. We need to convert that to grams, so that's going to be 0.01, or you can just multiply by 1 over 1,000, or you can just move the decimal place over 3 places to the left. Whatever is easier, but you've got to get it in grams. And then what you want to do, and let me just make sure that's right, yeah. You want to divide the number of grams, which is how much you have, by how much 1 mole weighs, which in this case is going to be 44 grams per mole. Let's see, 1, 2, 3, 0.01, yeah. So N is 14 and O is 16, but there's 2 O's, so it's 32 plus 14, which is, let's see, 16 plus 14 would be 40. 16 times 2 is 32, plus 14 is 42, 46, sorry. So NO2 is 46 grams per mole. Is that right? Let me do that one more time. 16 times 2 is 32, and 32 plus 14 is 42, 46, yeah. So we would divide how much we have by how much 1 mole weighs. So divide 0.01 grams by, I guess it's 46 here, and that will give us the number of moles. And then for A, it's just divide 150, which is how much we have, by whatever Fe2O3 weighs. I think Fe is about 56, so two of these Fe's would be 2 times 56, which is 112, and 3 times 16 for O would be 48. So 112 and 48 should be 160. So you divide 150, which is how much you have, by 160, which is how much 1 mole weighs, and that's almost 1 mole, like 0.95 moles or something like that. So let's go to the next slide, and then let's go to the next slide. All right, here's one of our empirical formula problems. So notice here that it gives us something that has only CH and O, and it tells us that we've got C is 48.64% and H is 8.16% by mass. They don't give us O, but we can figure out O by subtracting 100 minus 48.64 minus 8.16. And whatever's left over out of that is going to be your O. So just roughly, it's going to be 49 and 8 is 50. See, 49 and 8 is 57, so that would leave 43. So the O here is going to be about 43%. Remember, on this kind of problem, you just have to remember to change it to grams. This is going to be about 43%. So you would change the O to 43 grams, the C to 48.64 grams, and the H to 8.16 grams. I'm just changing the percent to grams. And you're allowed to do that. In this case, because what you're doing here is you're setting up the problem. And then divide each one of those number of grams, for example, for carbon. And you do the same thing for all three of these. You would divide 48.64 grams by 12, which is the gram atomic mass for carbon. And that's going to be just about exactly 4. Okay, do the same thing for your H here. 8.16 divided by 1 would be about 8, a little over 8. And then 43 roughly divided by 16, whatever you get there. And then the next step, you just have to remember that whatever the 3 numbers of moles are, you find the lowest number and divide through all of those numbers of moles by the lowest number. And when you do that, you'll get the empirical formula, and they're not asking for the molecular formula. So this is all we have to do for this one. So just the empirical formula. Let's go to the next slide. So O turned out to be 43.2% when you subtracted these numbers here from 100. So here is your O percentage. You change that to grams, divide by 16, and that will give you the number of moles of O, and it's 2.7. For carbon, as we said, it's going to be about 4, and it's actually 4.05, and the H is 8.16. Now we want to choose this, or this number, the one that's the lowest, which in this case will be the 2.7. And then we'll divide all three of the numbers that I just indicated by 2.7. You just have to remember that. I just have to remember to do that. So when we divide 2.7 by itself, we get 1. So O is going to be 1. C is going to be 4.05 divided by 2.7, which is here, which is 1.5, almost exactly 1.5. And H, 8.16 divided by 2.7. Here is about 3, almost exactly 3. So just write H3, O 1, and C 1.5, which I've written over here. So C 1.5, and these numbers that are at the subscripts at the bottom of these letters, 1.5 and 3, are just coming from what we did here. So the 3 comes from right here, and the 1.5 comes from over here. And that's your empirical formula, but you usually don't want to leave it like that with a fraction. So to get rid of the fraction here, the 1.5 is a fraction. You want to get rid of that. So multiply it by 2, but you can't just multiply that C by 2. You also have to multiply the 3 under the H by 2 and the 1 under the O by 2. So you're going to wind up with C3H6O2, and that's actually going to be the empirical formula. That's not the molecular. So if they asked you to do the molecular formula, you would have to figure out what this weighs by saying, okay, 2 plus 16 plus 6 plus 6 times 1 plus 3 times 12, whatever that is. See what it is. So that would be 36 and 32. So it would be 74. So if the molecule that you had weighed 74, then that would also be the molecular formula, C3H6O2. But if it weighed twice that, which would be 148, then you would have to, again, multiply all these by 2 to get it up to the right number for that molecule. Next slide. All right, so what we just did with the empirical formula is guaranteed going to be in the final and also on my exam. All right, balance the following equation. Let's do the first two. So look at the calciums. This is not balanced. Look at the calciums on the left and the right. 3 on the left, on the right, and 1 on the left. 3 on the right, 3 calciums on the right, and 1 on the left. So they're not balanced. And we don't have anything by itself on this one, so we can't like leave anything to the end. But I am going to go ahead and do the way I do this the way I usually do, which is to do the main things first. Which in this case, the main things, in my opinion, are the P and the CA. And then I usually leave the things like the O and the H to the end if I can, even though we don't have a situation where we have like O2 or H2 by itself here. So for CA, we have 3 on the right, but only 1 on the left. So let's put a 3 here, and let's see if that helps any. Sometimes it will, sometimes it won't. And then for P, we have 2 on the right and only 1 on the left, right? So we have to put a 2 here. Okay, and then in order for that to work, the O's and H's also have to be balanced. So the H's on the left now, we have 2 here, and we have 2 times 3 is 6 here, so we have 8 total. So we would want to put a 4 in front of the H2O so that we would have 8 H's, because there are no H's in this thing. And then it turns out that that balances everything else. It won't always happen that easily, but in this case it did. And then let's do this one, and I'll leave C for you to do on your own. AL, we have 1 on the left and we have 1 on the right, so it's good for the time being. For CL, we have 3 on the right and only 1 on the left. So let's put a 3 here. So now the CLs are balanced and the ALs are balanced. So let's go now to the H's again. So here we have 3 H's and here we have 3 H's after we put the 3 in here. So 3 and 3 is 6, so we want to have a 3 here in front of the H2 to give it 6. And again, that turns out to do the job. So putting the 3 in front of the HCl and in front of the H2O fixes that one completely, and the O's are also balanced. So you can go ahead and look at the O's also, but you're going to wind up with 3 O's on both sides. And so those two are done. And I'm going to let you do this one the same way. So do it on your own. The way you would start off basically would be to do the AG and the S. So you have 2 AGs here, so you'll want to put a 2 here to start with, but you may not end up with the 2 there, but you want to start off that way. S's are already balanced. Oh, and then the N's. So when you put the 2 here in front of this thing, you mess up the N's because now you have 2 N's on the left, so you want to put a 2 here. And then go ahead and just finish it up. So next slide. Next. All right, here we come to a very interesting problem that I've asked many times on tests in the past. A given sample of xenon fluoride compound contains molecules of the type XeFN, and we're supposed to figure out what the N is. So, I mean, it could be XeF2 or 3 or 4 or 5 or 6 or whatever. So what is N? So our question is, what is N? So xenon, if you look at the chart, it has a certain atomic mass. So let me just write a question mark here. I'm trying to write and talk at the same time. All right, so this is a very easy problem to do. First of all, the total mass of all of these molecules, which we know how many there are, there's 9 times 10 to the 20th. The total mass of that is 0.368 grams. So we divide 0.368 grams by roughly 9 times 10 to the 20th molecules, and that's going to give us how much each molecule weighs in grams. So divide 0.368 grams by 9 times 10 to the 20th, and you're going to get some really tiny number of grams, and that's how much each of those molecules weighs or has a mass. All right, and then what we're going to have to do, though, is we don't want the mass of each molecule of XeFN. We don't want it to be in grams. We want it to be in atomic mass units. But we have a conversion factor, and that's 1.66 times 10 to the minus 24th grams is 1 AMU. So you want to use your conversion factor and do dimensional analysis to get whatever you get when you do this division right here in grams. You want to multiply that by grams on the bottom and AMUs on the top of a fraction. So you would have 1 AMU on the top, and you would have 1.66 E minus 24 grams on the bottom, and the grams cancel, and you get a number of AMUs. And I can't remember exactly what that is, so we'll look at that in a moment. And then just look up the mass of xenon in your chart. Remember to look up the mass, not the atomic number. And then subtract that number from whatever the number was that you got over here. So let's go ahead without further ado and go to the answer slide. So we wound up here, when we divided 0.368 grams by 9.03 times 10 to the 20th, we got 4.0753 excuse me, times 10 to the minus 22nd grams, and that's 1 molecule's mass. And then we want to convert that to its mass in AMUs by multiplying by your conversion factor here, which will be given to you on the test. And when we do that, we see that we get 245.42 AMUs. So that means there's 245.42 protons and neutrons in this. And if we look up the mass of the xenon, and if I do that, I see that it comes out to be 131.3. So I want to subtract that away from the mass of the whole thing, so that everything that's left over is just going to be the mass of the fluorines. So we want to subtract 245.42 minus 131.3, and when we do that, we get 114.12, and that's the mass of the fluorine. So if we knew how much one fluorine weighed, we could just divide 114 by that mass, and we're going to get the number of fluorines, right? So look at the chart and see what fluorine weighs, and it turns out that it weighs 19 approximately AMUs. So just divide 114 by 19 and you get approximately 6. So that means that N is going to be 6 here. Okay, next slide. All right, for these weighted averages, all you have to do is convert your percentages here, which they've already done. No, they haven't done that. So these abundances are in percentages, so we have to convert those to fractions by getting rid of the percent sign and then moving the decimal place back over to the left 2 places, or just multiply by 1 over 100, or just divide by 100. So this one on top is going to be 0.0507, this one's going to be 0.1535, and this one's going to be 0.7985, and I'm going to multiply that 0.7985 times that number 0.1535 by this number and 0.0507 by this number, and add them together, and that's all you have to do. So, I mean, if you look here, you can see that most of this is this 42 isotope here, so this is most of it, about 80% of it. There's a little bit that's a lighter element, and then there's a little bit that's a lighter yet element. So the mass here is going to be less than 42.111. If it were all 42, then it would all be 42.111, but it's not going to be that high. It's going to be a little less than that. So I'm going to guess it's going to be between 41 and 42, and there's only one answer here that matches that description, and that's E. So E is going to be your answer without having even to do the math. But if you wanted to do the math, you would multiply 0.0507 times 37.919, 0.1535 times 39.017, and 0.7985 times 42.111, and add them together. And you should get 41.54. And it turns out that you do get 41.54. Next slide. The mass percent of carbon is going to be the mass of the carbon divided by the total mass. So the total mass here is going to be S, which is 32. Let's see, and O is 16. So 32, 16, 6 times 1 is 6, and 2 times 12 is 24. So you would just add all those up, which whatever that is. I mean, I can do it in my head. So 24, 40, 72, so I think it's 78. And then, so what you want to do, that's the total mass of the whole thing. And you want to divide the mass of the carbons, because we're looking for carbon here. And that would be 2 times 24, because carbon is 12. So you would be dividing 24 by 78. And that, whatever decimal you get, you multiply by 100%. So 24 over 78, that reduces to 12 over 39. So it's a little bit less than 1/3. So it's a little bit less than 0.33 or 33%. So it looks like the answer is probably going to be this one, but you should do it on your calculator. Just divide 24 by 78. That's going to give you a decimal. And I'm going to say that it's going to give you a decimal of 0.307. So 0.307, to convert that to a percentage, you just multiply by 100%. Next slide. And so when you do that, you get, actually I got 30.8%, but there's only one answer choice between A and E up here that's even close to that, and that's E. Next slide. All right, and then we have a couple of stoichiometry problems. So what we're going to want to do for these is find the limiting reactant. So we have, over here, we have aluminum and O2 that could be the limiting reactant. So we want to, first of all, figure out which one is. I mean, if we wanted to guess, we'd probably say it's going to be the aluminum, because O2, unless you have it in a closed container, there's an infinite, basically, amount of O2. But let's just do it anyway. So let's do the limiting reactant part, and then we'll do the rest of the problem. So we have 2.5 grams of aluminum, and aluminum, and I'm trying desperately to think of what its mass is, because it's one of the ones I don't use that much. So I can't remember, and I don't really want to flip over to the answer yet. So anyway, let me just say it this way. Whatever the mass is of aluminum when you look at the chart, divide 2.5 grams by that mass. So anyway, and that'll give you the number of moles of Al. And then do the same thing for the O2. So we have 2.5 grams of O2, so you want to divide 2.5 grams by 32. And that will give you the number of moles of O2. Now, the way that you're going to do this, and I think it's actually going to be easier for you to see this if I go to the next slide, so let's do that. So, all right, so the aluminum was 27 grams per mole. So when we divide the 2.5 that we have by 27 grams that it takes to make 1 mole, we get about 0.1, it's actually 0.09259 moles of aluminum. So the aluminum was 0.09, and then the O2 is 2.5 that we have divided by 32, which is how much it takes to make 1 mole, and that's 0.078. Now, to do the limiting reactant, you want to look at the relationship between the coefficients here. So you can do it either by starting with the aluminum and working to the O2, or you can do it in the reverse. I'm going to do it, let's see, the easiest way to do this, I think, is going to be to start with the O2. So let's start with the O2. So how many moles do we have of O2? Well, we just figured it out. It's 0.078125. So in order for all of the O2 to react and all the aluminum to act, react, we'd have to have 4/3 as many moles of aluminum as we do of the O2, which means if you multiply the 0.078125 by 4/3, that's going to tell you how many moles you would need of aluminum. And if you did that, you would get 0.1042 moles of aluminum. That's how much you would need to react with all the O2. So look back and see if you have that much. Do you have that much? No, you don't quite have that much. Almost, but no cigar, right? So we need 0.1042. We've only got 0.09 something. So we don't have enough aluminum. So we're going to write limiting reactant LR over above the aluminum here. Now you don't have to do it the way I just did it. You could also have started with the number of moles of aluminum that you have and multiply that by 3/4 to see if you have enough O2. And if you did that, in other words, you would multiply this number, 0.09259, by 3/4. And if you did that, you would see that you have more than enough O2. So the answer would still be that the aluminum is going to run out first. Now to go ahead and finish the problem, we're going to just use this and not the O2. So the aluminum is the one that's going to run out first. So just for right now, we can just kind of forget about the O2 and just use the aluminum. And so what we need to know is how many moles do we have of aluminum? Well, we've already figured it out. It's 0.09259. So just look at your relationship between the coefficient in front of aluminum and the coefficient in front of the Al2O3, because what we're trying to do is figure out how much we can make of the Al2O3. Okay, so we'll come back to this part over here later. But that's what we're trying to figure out. So what's the relationship between the coefficient in front of aluminum and the coefficient in front of your product? Well, one of them is 4 and one of them is 2. So in other words, you only need let me say it a different way. You can only make half as much Al2O3 in terms of the moles as you have of the aluminum. We know how much we have of the aluminum. We have 0.09259 moles. So we can just actually divide that by 2, this number right here, and that will tell us how many moles we can make of Al2O3, and then we'll figure out what the molar mass is of Al2O3 and multiply that by the number of moles. So down here, we multiply 1/2 times the number of moles of aluminum, and that gives us 0.046 moles of the product that we can make. Again, that's because of this 4-2 relationship. We can only make half as many moles of the product as we have of the aluminum. And then to get that over to grams, you just multiply the 0.046295 moles times however much that weighs. So you'd have to multiply the atomic mass of aluminum times 2, and then 3 times 16 here, and add them together. And when you do that, evidently you get 102. So you multiply 102 times 0.046295, and you get that you would be able to make 4.72 grams according to the equation. In other words, according to the paper, which we call that either a priori or theoretical. And those both mean the same thing. So this is how much we could make, in other words, in a perfect experiment, but they actually did the experiment and they only produced 3.5 grams. So the yield would be how much they actually did make divided by how much you could have made in a perfect experiment, which is 4.72 grams. So divide 3.5 grams by 4.72 grams, and that's going to give you about 0.742 as your decimal. And then you multiply that by 100% to convert it to a percentage, and you get 74%. So let's go to the next slide. And then here's another one that's similar to this, and we can't just look at this and say, oh, there's O2. That's going to be excess, so we'll have to do the same thing we did in the previous problem. We have to find the limiting reactant. So let's go ahead and do that. For both of the reactants, which that would be the magnesium and the water, we want to divide how much we have by how much 1 mole weighs. Now we know that 1 mole of water weighs 18. So 18 grams per mole for the water, and we have 1.83, so we have about 1/10 of a mole. For the magnesium, 4.73 is how much we have, so we divide that by 24.3, because I happen to remember that one. The atomic mass for magnesium is 24.3, so we divide that, so about 5 divided by about 20, so it's about 0.2 moles. So we have about 0.1, so let me see if I can write that. My hands are real sweaty and I'm having a hard time getting this thing to work. But about 0.1 mole of water, and what did I say, 0.2 moles roughly, these are very rough, 0.2 moles of magnesium. So now look at your coefficients. If you have, this time why don't we start with the magnesium. If we have 0.2 moles of magnesium here, how many moles would we have to have of the water to react with it? We'd have to have twice as much, because for every 1 mole of magnesium we have to have 2 moles of water. So we would have to have 2 times 0.2. Let me see if I can write this, because when my hands are wet it doesn't work very well. Times, actually that's supposed to be times 2. So 0.2 times 2 is going to be 0.4 moles is how much we'd have to have of the water. But we don't have that. We've only got 0.1. So we don't have nearly as much of the water as we need to have. So the water is going to be the limiting reactant. So let's write that. And then once we've determined that, what we can do is start with how many moles we have of the water, which is about 0.1. And we'll look at the exact numbers in a moment. And then look at the stoichiometry for the 2 here in front of the water and the 1 implied in front of the H2. In other words, how much H2 can we make? Because that's what they're actually asking. Well, we can make half as much H2 in terms of the number of moles as we have of the water. We've only got about 0.1 mole of the water, so we can only make half that much H2. In other words, we can only make about what you would get if you divide 0.1 by 2, you could get about 0.05 moles of H2. And that's the number of moles of H2, which I'm not going to even try to write all that out because it'll take too much time. And then you would then multiply that to get the mass. You would then multiply that by the mass of H2. Well, H is 1, but H2 is 2 times 1, which is 2. So you would then multiply that by 2 grams per mole. And when you multiply 2 times 0.05, you get 0.1. So equals 0.1 moles. And all of this is done, and the numbers are exact. So you get 0.1 grams of H2 from this process. So what you need to really watch here is that very first step, because if you take off and start doing the problem without first figuring out which one of those 2 reactants is going to run out first, you're very possibly going to get the wrong answer. You got a 50-50 chance. So just don't take the 50-50 chance. Just stop and figure out, okay, how many moles do I have of magnesium? How many moles do I have of water? And then look at the coefficients. If I have this many moles of magnesium, how many would I have to have of water? And the answer, I'd have to have twice as many moles of water. So see, do you have twice as many moles of water? In this case, we didn't. So we had to assume that water's going to run out first, so we call that the limiting reactant. And that's really maybe the hardest part of the whole problem. And then once you know that this is the one that's going to run out first, you want to use this one to figure out how much product you can make, whether they ask for magnesium hydroxide or whether they ask for H2. Now in this case they asked for H2. So we wound up with an answer here, just doing it roughly. We said it was about 0.1 grams. We have an answer choice here that's close to that, so I'm going to go with D. Next slide. And it turns out that that's actually correct. So let's go to the next slide. And we're done. And it is right at a half an hour, which is about reasonable for this particular chapter. So just in these last few seconds, let me just say this. I recommend that you go back through the problems we did in the lecture notes. There were several of them. And actually they were harder, I think, and maybe you'll agree, than the ones that we just did in the work problems here, because you had to do more things. But anyway, I would go back through the ones in the lecture notes, especially the ones towards the end of the lecture notes, like those last 2 problems. And then I would go through these problems, but there's not that many here. This is really a short set of work problems. It's probably the shortest one that we'll do this semester. So I would go through these though first and make sure you're really good at them, completely understand them, and then one at a time start to add to that by visiting other websites that have sample problems in stoichiometry, or again, as I've said many times, go to Mr. Mack's website. So find the chapter on stoichiometry. It should be one of the first chapters, and you'll find that he'll have a test there, and you can just go to that test and scroll down, and he'll have a whole bunch of multiple choice questions that you can do, and just do those for practice. And let's go ahead and call it a chapter here. So that ends chapter 3, and we'll see you in chapter 4.